In this world, liquids can talk. Once united in the great container, they kept the balance of flow and form. Now the bonds are broken, and only one will pour into legend. Wait, what even is viscosity?
Hi there, I'm Chloe, and today we are diving into something that affects everything from syrup on pancakes to lava from volcanoes. Let's explore what makes some liquids flow fast and others slow. Viscosity is a liquid's resistance to flow. A low viscosity liquid, like water, flows easily. A high viscosity liquid, like honey, moves slowly and thickly. This happens because of how the molecules inside the liquid interact, which brings us to the real stars of the show. IMFAs, intermolecular forces of attraction, are the forces that pull molecules toward each other in a substance. They're not chemical bonds, but they're strong enough to affect how substances behave. There are three main types you should know. Dipole-to-dipole interactions. These happen between polar molecules, molecules with positive and negative ends. The opposite charges attract, but the forces are moderate in strength. Hydrogen bonding. This is a special kind of dipole interaction. It happens when hydrogen is bonded to highly electronegative atoms like oxygen, nitrogen, or fluorine. Water molecules use hydrogen bonding. These bonds are weak and temporary. That's why water flows so easily. It has low viscosity. These are the weakest IMFAs. They occur between all molecules but are especially noticeable in large, non-polar ones like oils. Because they're weak, molecules can slide by, but the long molecular shape still creates resistance. In contrast, honey contains sugars like glucose and fructose. These molecules form strong hydrogen bonds with each other, making the liquid thick and slow-moving. Dish soap has surfactants, special molecules with both polar and non-polar parts. They disrupt the forces between other molecules. This reduces surface tension but can actually increase internal friction, making it flow slowly in bulk. Viscosity isn't just for science class. It affects our daily lives. Motor oil needs the right viscosity to lubricate moving parts. Too thin and it won't protect the engine. Too thick and it won't circulate properly. Syrup flows better when it's warm because heat breaks some IMFAs, lowering the viscosity. In geology, lava viscosity determines eruption style. Thin lava flows fast and spreads. Thick lava traps gases, building pressure for explosive eruptions. So, the next time you watch syrup drizzle or see a volcano erupt, remember, it's all about IMFAs and how molecules interact. I'm Chloe. Thanks for learning with me. Bye-bye and see you again next time.
Okay, now that we understand, let's continue on to the race. And the winner for today's race is water.
Have you ever wondered why honey flows like it's half asleep, while water rushes in like it's late for class?
Why do some liquids flow faster than others? Is there a science behind this?
The answer to Sam's question isn't new. In fact, it started centuries ago. Isaac Newton, in 1687, first described what we now call Newtonian fluids, liquids where viscosity stays constant regardless of how fast you stir them. Later, in the 1800s, Jean-Léonard Marie Poissy studied how blood flows through narrow tubes. He, along with Gotthelf Hagen, gave us the famous Hagen-Poissy equation. It helped explain how pressure, radius, and fluid thickness affect flow. And George Stokes? He observed how spheres fall through liquids, laying the groundwork for a hands-on method of measuring viscosity. In this footage, we tested different liquids by dropping a marble and measuring the time it took to hit the bottom. In water, the marble zips down. In honey, it barely moves. The difference? Resistance, molecular resistance, what scientists call viscosity.
So, viscosity isn't just about thickness. It's about how much a liquid resists flow. It's measurable, it's predictable, and it's fascinating.
Viscosity is more than just a property. It's a principle that governs how fluids behave, from tiny capillaries in our bodies to massive rivers carving the earth. In real life, viscosity matters more than we realize. Ketchup is a shear thinning fluid. Shake it and it flows. Don't and it sticks. Engine oil needs the right viscosity to protect your car engine. Too thick and it won't flow. Too thin and it won't protect. The viscosity of magma determines whether a volcano will erupt gently or explosively. And in our bodies, blood viscosity affects how easily it flows through our veins, and even our blood pressure. So the next time you pour syrup on pancakes or watch raindrops slide down a window, remember, viscosity is everywhere, unseen but always in motion. This is viscosity, the science of how things flow. And now you know.